What's going on, Basement Hackers? Sorry, I was taking a minute to get everything working. I'm ready to dive into it. I was going to look a little bit at this document that we found last time. That was the ELF, kind of the full guide to the ELF, yeah, the executable and linking format ELF format is. Let's just get into it, and we could skim through this. It's like 100 pages, but it seemed like it was quick to go through. So I'll just kind of read the beginning, and once it gets into the annoying stuff, then we'll kind of skip. And I want to get into looking up the emulator machine as soon as we can. So, introduction. This chapter describes the object file format called ELF. Executable and linking format. There are three main types of object files. The relocatable file holds code and data suitable for linking with other object files to create an executable or a shared object file. Okay, an executable file, which holds a program suitable for execution. A shared object file holds code and data suitable for linking in two contexts. First, the link editor may process it with other relocatable and shared object files to create another object file. Second, the dynamic linker may combines it with an executable file and other shared objects to create a process image. So we know, like, shared objects, you'll use them. It's good for if you want to be able to update them after the fact. You can update a shared object, and as long as the binary interface stays the same, it'll still work. But you might fix bugs inside it. You also might want shared objects when a shared object is shared across multiple programs or process images on your operating system. There's efficiencies where you can load that shared object into memory once and run it, like multiple applications can use it. That's more if you're resource constrained in that sense, but since we're not using an operating system which would manage something like that in an embedded bare metal scenario, we wouldn't really benefit from that. The relocatable file would probably be like a .a file, like an archive file, and then executable would just be your exe or your runnable program. Created by the assembler and linker editor, object files are binary representations of programs intended to execute directly on a processor. Programs that require other abstract machines are excluded. After the introduction material, this chapter focuses on the file format and how it pertains to building programs. Chapter 2 also describes parts of the object file, concentrating on the information necessary to execute a program. Alright, so here's the general format. So file format, object files participate in program linking, building a program. So we've seen that we've been building object files doing the first three phases of compiling, which is preprocessor, compile, assemble. And once you run it through the assembler, you'll have assembly at the other end that makes in an object file format. And program execution, running a program. So once you get it linking, you can now have a runnable instance. For convenience and efficiency, the object file format provides parallel views of the file's contents, reflecting the differing needs of these activities. Figure 1.1 shows an object file's organization. So let's look at the linking view. Let me just make sure chat's all running smooth. I didn't verify it. Sorry. make sure everything is working. Alright, it sounds like it's working good. Alright, so program header table, and it's optional. Then you can have sections, and we learned about input sections and output sections. I wonder if that's what these are, because these are called segments here. Sections header table. Okay, and then there is a sections header table, which is optional in the execution view. They both have the header the elf header. Program header table. It's not optional in an executable program. So that's interesting. So, okay, and then segments versus sections. All right. So introduction: an elf header resides at the beginning and holds a roadmap describing the file's organization. Sections hold the bulk of object file information for the linking view. Instructions, data, symbol table, relocation information, and so on. Descriptions of special sections appear later in this section. Chapter 2 also describes segments and the program execution view of the file. A program header table, if present, tells the system how to create a process image. Files used to create a process image, execute a program. Files used to build a process image, execute a program, must have a program header table. Relocatable files do not need one. A section header table contains information describing the file's sections. Okay, that makes sense. Every section has an entry in the table. Each entry gives information such as the section name, the size, and so on. Files used during linking must have a section header table. Other object files may or may not have one. So of course you're going to need the name, because that's how we reference it in the linker. And then the section size, that we reference a lot when I think you can do like the size thing in the linker command, or length. I think it's size, and so on. Alright, note, although the figure shows the program header table immediately after the elf header and the section header table following the sections, actual files may differ. Moreover, sections and segments have no specified order. Only the elf header has the fixed position in the file. So the header must have where to go look, and like an index in, and so forth, to find those these header tables. The section header table and the program header table. Data representation. As described here, the object file format supports various processors with 8-bit bytes and 32-bit architectures. I was worried it was about to say 32-bit bytes, and then I was going to get really confused. Nevertheless, it is intended to be extensible to large or small architectures. Object files, therefore, represent some control data with a machine-independent format, making it possible to identify object files and interpret their contents in a common way. Remaining data in an object file use the encoding of the target processor, so little or big endian, I'm assuming, or half word, full word, signed word, okay, regardless of the machine on which the file was created. Wait, wouldn't the whole thing have to be? Well, I guess no, because you could be cross-compiling or Canadian compiling. You really applies to cross-compiling. Canadian compiling is just where you're compiling a tool chain that's not going to run on your on the system you're compiling on. You're building the tool chain to run on a different system to then compile for another system. It's weird. usually you'll build a tool chain on the same system you're probably going to run on, and then you're just going to build a tool chain and then cross compile using that tool chain. But look at the Wikipedia; it's pretty funny. I don't know why Canadian. I think it says it on the wiki, but it is a thing. So the elf, I'm going to keep saying elf wrong. I feel like I'm saying it weird. So you can have unsigned program address. You can have unsigned medium integer. So these are the 32-bit data types. Signed large word, unsigned large word. It's really weird that this is 32, but it's a half. Is it really L32 because just the header is in 32 and then the data is really in 2? Probably something like that. All data structures that the object file format defines follow the natural size and alignment guidelines for the relevant class. If necessary, data structures contain explicit padding to ensure 4-byte alignment for byte objects, to force structure sizes to a multiple of 4, and so on. Data also has suitable alignment from the beginning of the file. Thus, for example, a structure containing a 32-bit address, an ELF 32-bit 32 address member will align on a 4-byte boundary within the file. For portability reasons, ELF uses no bit fields. Alright. This is kind of getting a little bit into some nitty gritty. I was thinking it was worth coming in through here, but maybe it's not. Because we did see some of these referenced within the linker script. Like if you do, actually, like we definitely saw some of these being referenced. I think we saw e-entry referenced. Gives the virtual address to which the system's first transfers control, thus starting the process. Then we saw that. Let's open up our project, and I think that was in. Let's see if this reopens to where I left it, because I restarted my machine. Looks like it will. We have that 0 to main tutorial that we did last time. I think he referenced this in source code. If the file has no associated entry point, the member holds 0. What's this thing doing? It's a text editor. How hard is it to open? Alright. Let's see if I can see what I'm thinking about. This was their reset handler. I think this is where they reference something like that. These were symbols that we defined in the linker script, or he did, but I'm going to say we, being that we edited it and messed with it. We'll start his startup. I think it's minimal. Could have sworn I saw him use one last time. I wonder where I saw it. I remember seeing it, but okay. Maybe it's not. I kind of want to just go do the more fun thing. Seeing if any of this looks good. So here's what we're going to do. We're going to go find... I have a lot of things open from last time. I want to find where... We wanted to find this before, I think, 7. And I think we wanted 7E. But this will tell us about the entry points into that type of architecture. We don't need this. And this was just the... I'm going to put this on the end. So we know we want to get that emulator. Let's get the actual name. So QEMU. Why is Quick Emulator not running? Or not in the path? I wasn't SSH'd in. Hopefully this isn't a problem. Come on. What was the machine we were doing it for? And for some reason, my hardware still hasn't come. I gotta check on the order. So I'm pretty sure they charged me. Is the first place to go in case you have questions about using the Quick Emulator. Most of the documentation is generally generated automatically from the source, or some text files cannot be converted properly. So let's go here. Assistant Emulation User's Guide. User Mode Emulation User's Guide. This manual is the overall guide for users using the Quick Emulator for user mode emulation. Must not be running. So So this is talking about A8. The chip we're getting, I have that open in another window. We're getting a TM4C 1294. Versatile, I think, was what we were looking at. So let me see. This doesn't really talk about TI specifically. It's QEMU. ARM System Emulator. Like boot up. Try to find my Vagrant is having problems again. It's always something on. I just can't stand my Windows machine. It doesn't really even show like linking or anything. No, he's just actually running it inside that. So this one has some linking. C and ARM emulating execution. They're doing versatile PB. I can't remember if that's the one for, because I know that's one we looked at, but I'm not sure if that's the one we want or if that's what the other example project was doing. So they do some assembly on these guys, startup code and stuff. They compile, then they link all those together. They copy it into a bin file or to bin file. Then they run the emulator with the -S and -S, which does like tells it to run on localhost GDB, and the other one says to not start the application right away, and no graphics says not. Yeah, there's no graphics. So I mean, they go to that same offset here, and they do the startup code. Not sure what the division's about. Alright, let me see. I'm hoping this isn't a problem. I just want to go on there to see the architecture and everything that we're supposed to be using. I can't remember which one it is for TI. I guess I can look at this and remember what this was for. Machine has also often been used as a general-purpose Linux target for in the past. Yeah, so I don't think I want that one actually. What was the one for the Intel TI? I mean. It's not even in the list. I think it was like one of these two. Yeah, it was this. It was this one. So I want to see stuff on that. Does it mention it anywhere else here? As well as a more common A profile CPUs. We also support the M3 and M4 M profile CPUs, which are microcontrollers used for very embedded boards. We only have 2 boards which use the M profile CPUs at the moment. Okay, cool. The TI Stellaris evaluation boards. Okay, so I want to look up about that. Let me just try the basic. Give me docs for it. Alright, so here are the two. The Luminary, Micro Stellaris, whatever emulation includes the following devices. They're M3 CPU cores, 64K flash, timers, UARTs, ADC, I2C. I think we're doing this one, which has a few of the other ones. So that's cool, but now I want to know more about the actual architecture. I guess that's all they're going to really tell me here. Let me look at it again. So we could go to here. Oh no, this is. I do want that Git repo, GitHub, I think. Let's see what this guy is. So here's a data sheet for the micro. We can look at the startup here, and that might help us. It's probably not going to talk about the startup code. SRAM is at that 2 million hex. On-chip flash starts at 0. So this memory layout does matter. And these addresses, we definitely want to bookmark this guy. Then like all the memory mapped registers. Static RAM. I just wanted to learn about the startup. I wonder if that would just be a TI startup thing. What are all the sections? Let's start with that. Alright, instead of scrolling like a madman. Alright, so their intro, they're going to have audience, all that stuff. Product features, target applications, high-level block diagram. Look at that. JTAG hooks straight to it, or serial wire debug. There's flash. This is all a solution, SOP, right? SOC, or system on a chip, or solution in a package, or has an NVIC, so it has power management, memory management, bus matrix. So this, here's the internal RAM, system clocks and stuff, hibernation module, watchdog timer, GPIO, or general purpose timers, GPIOs, I2C, UARTs, another serial interface, Ethernet, MAC, and PHY, analog comparator, PWM, quadrature encoding? I think that's what it is. Yeah, motor control. 10-bit ADC, and then possibly more. Okay. Let's go back to the top. I just wanted to see the block diagram. I know the boards we're getting are M4s, but they should be very similar. A memory map lists the location of the instructions and the data in memory. The memory map for the controller can be found. I think we probably saw it. Register addresses are given as a hexadecimal increment relative to the module space address as shown in the memory map. Oh, this is going through all the block diagram parts. This is actually pretty well laid out. Microcontrol. I like how their flow of documentation actually. It's ARM7, not ARM7E. Migration from the ARM7. Oh, what? Maybe it is ARM7E. Oh, memory protection unit, yeah. Thumb 2. So, I wonder... Question on a bootloader sample code. This is talking about their eval kit. Come on. I'm trying to think of even how to ask the question that we're trying to do. This is the same thing we have here, right? Where's power on flow or something like that? These are just every figure they have. Not sure a good way to look into this. Let me see if anyone has a project for this. It's probably gonna be a Rust one anyway. Organize your issues. So here's somebody doing, what is this? Embedded systems architecture? Okay. Quick emulator, and they're trying to do that with a binary image. But they're just talking about emulators. Here they define the size. Here's a linker script. Put all the text in Flash. Start text. 5 years ago. We're both M3 based and support a related machine in QEMU. Adding support for these boards will let us run unit tests, etc. for the hardware. So this is when they were doing the work, it looks like, for still don't understand how they understand the startup sequence. Oh, it's probably under ARM. No. One thing we could do is just look for that weird address. No. Target applications. I'm seeing if there's anything that'll tell us how it starts. System level interface, traceport interface. It'd probably be in like a power on reset like section. Different registers. Where's their power management? Because maybe system control. Resets the JTAG controller, and external reset does not. The POR circuit monitors the supply voltage. It loads the initial stack pointer, the initial program counter, and the first instruction designated by the program counter, and then begins execution. The internal reset is released and the core loads from memory the initial set. Yeah. See if this thing is up by now. This is gonna drive me nuts. Software reset, brownout reset, power on reset. They said it's not the exact same as an internal reset. Well, the internal power on reset circuit and the power supply voltage generate the reset signal. Specific operating parameters when the on-chip power on reset pulse is complete. The micro must reach 3 volts. For applications that require the use of an external reset signal to hold the microchip. So you can have an external reset, a power on reset, a brownout, software initiated reset, and a watchdog. They should all boot like it said, but it doesn't really give us addresses to things and really talk about that flow. Says this thing's running. Oh, we got a show. Didn't mount the shared folder. Let me just see if fdisk. What? See, it's supposed to have a shared folder. It's supposed to be mounted. So what the hell? I forget what the hell. I'm just trying to see if I can mount it manually. If it's even there. SBD, SDA1. What is it called? D-message? What did D-message say about SDA1? Tail less. Mounted file system from somewhere else. I'm going to try to mount that and see if that mounts. Dev SDA1 to Vagrant. I thought that was it. Just make me sudo, God. Like 10 gigs. SDA is 10 gig. Oh my God. I'm just gonna try some of the other ones. That's already mounted. I forget how to even ask what machine it is. You just do it without. But there was like. Oh, you just do help. Yeah, and then we know we're going to be this Solaris guy. And then we would do I hate this. 3S 6965 VB. And we're just doing a Cortex M3. But I don't even know what I'm trying to accomplish now. I mean, we want to go look at the quick emulator and look at the source code. So let's go to GitHub and try that. I'm not able to mount my source code from my host machine there, but we don't have to have that for right now. If I remember right, it's under like boards and then ARM. No, it was under art, like platform. Where is it? Where is it? Virtual IO FSD. I don't think it's in here. Is it? No. Hardware ARM. How did I not see ARM when I was looking through it? Okay, so we wanted to look at this and how it's going to reference things. I think we started even capturing some notes on it. I'm like trying to remember where we left off. So let's close that guy. We're going to do it in here. Let's close all this. And we started writing startup code that was just generic based on other stuff. C entry. This is where I was thinking about it earlier. And this looks very similar to what a lot of the examples we've seen are. And this is what we wrote before. These are the right size. Let's see if that's what the size that they think it is. Let's look at the tombstone first. So nothing really GPL license. Alright. I know we saved notes. Where the hell did I put all those? Oh, and we did check out Quick Emulator, so we do have that here. We'll start more notes again, unless we can find them. Because I remember last time, or one of the other times, we went in here and we got they have a section somewhere here that they lay out how they initialize the. Let me look for init. No, it's I squared C init, ADC init. Let's go to top. General purpose timers. This is where they bootstrap it into the rest of the system. Just one that we saw. This is how it will find it when you give command line options based on this name. System init. Most devices come pre-programmed with a MAC address, memory region. So here's where they're having. I wonder what this is. So in our system init or sysinit, they reference 1000 hex on that last parameter, and same thing 1000 hex here for I2C. Not sure what that's about. This one's for an ADC though. This is for general purpose timers. Oh, I'm hitting multiple. I2C, ADC, general purpose timers, and then the sys. Where's this? Where's S? S is, oh. This is the layers. It's just a handle, but where is that system in it again? Sys in it. Because they're passing IO memory from this guy where we. So I need to look up some of the functions that are other places. Let's keep this open and open a second one. What we're going to do is look for some of these functions. So what does this guy do? I'm going to get everywhere it's called. I need where it is declared or defined. Let's think. How can I do that easily? We know it returns either a void pointer. Yeah, probably a void pointer. Oh, they do individual word mapping. That's so stupid. Or matching. That's so dumb. Unless I can quote it. Their search is so bad. God. I wonder if I can do that easier in here, because we should be able to seal this if we go to hardware, ARM, and then we go to the one for Stellaris. I haven't used Notepad++, but I know it has the ability to jump through code. So let's look at this function. Now let's try to go to this. I can at least do find in files. Let's do void star. Really? Alright, that should be in here. wasn't going to be as convenient as I expected it to be. Are you serious? Alright, I'm not ready for that. Call this a million places. Okay, what I want to understand is, so they do this whatever get new 0. I'm assuming it's just initializing something, and this is the type. Okay, so this is like a handle they're gonna pass around, I guess. Then they're going to just initialize these to everything that's passed in. So there's a MAC address, interrupt, IRQ handler board. I don't know if this is the actual register or what. Like a simulation for it. See, yeah, it looks like this is just like their new function. They're just dynamically allocating this with some wrapper. That's all it looks like. And then they're putting it here and passing it to different inits. So I wonder if this matches up. Okay. With the PDF that we have. Where is that? These are all the register bit defines. Want to be past all this. Just trying to see if we can get the overview page. Instruction set. Interrupts, how they're mapped. Yeah, this is what I wanted, the memory map. So looking at this side by side with that, like their watchdog timer is at 4,000. Okay. So this is aligning. This looks like it's lining up. GPO. I2C, which is unimplemented, is supposed to be here, but it looks like that's not there. There's another one at 2000 hex, which would be here, but they didn't do the I2C1. So this is lining up memory addresses to this. So that's good. Like, we know that this reference is going to match that well. I don't know how this will match the actual chip we have, and it probably won't. But we'll try to figure that out and maybe put a shim in between. So the flash size, what are they doing here? They're ending off the lower order, adding 1 to it, shifting it to the left once, multiplying by 1024, and the SRAM. So where does this DCO come from? So this is probably all stuff coming in from they have FF7F. So it's like the RAM size is in the lower 2 bytes and the flash size is in the upper 2 bytes is what it seems like. But they're actually using the size of it a little weird. So they're just getting rid of the zeros on the bottom, adding 1 to it, which if we look at that again, so this is the board we care about. So this would go away. They would add 1. It would roll it up to here, so it would be 0, 1. And then they shift it once to the left, so it would be that times 1024, which is 2 to the 10th. I can't remember. Yeah, it's 10 to the 10th. So we can just shift it over 10. I don't know, but that's good. It should match the size of the flash, and we know the flash was 256, right? 256 meg, and the SRAM was. Let's go back to the top of this. It was in the overview. Let me just go to here and then hit overview. Yeah, 256K. Oh, they're both K? Oh, wow, that's small. I'm trying to think. Maybe that is normal. I don't know. I can't think. What is this? Well, anyway, it's what it seems like it's doing. I don't understand why the lower order doesn't matter, but I guess. We still don't know how the startup code works, though. Alright, I'm going to take a break for the rest of the night because this is just frustrating me. I want to come back to it. We're going to start like right from here and try to get into how to figure out how it boots up. We'll just go into the quick emulator and try to run a line of code and step through the code as it tries to execute. Because I should be able to with GDB to step one line at a time. And we should see where the first like spot it steps into is. And then from there we can make it just call into our code at least and run our code, even if we don't do any of the BSS initialization or data initialization. So we'll do that next time, but I just can't right now. So we transition. Didn't have a great day today, but next time I think we know where to start. So that's good, and so we can start fresh. Maybe I'll try to get the next few days. I should have some time, and maybe I'll try to do one during the week. But if not, then on Sunday. Oh no, Sunday is Father's Day. I probably won't be streaming this weekend, so I'll try to get one day in so we can get at least somewhere with this. So once we get past the hard part where it runs it all, we'll be able to do a lot of stuff. But this is definitely the hardest part. So until next time, try to hack in your basement, have some fun. Peace. Transition.